to QLab. In this video we're going to be exploring titration experiments. Now this is quite a complicated area of chemistry, and as such this video is going to be quite long. But if you are wanting to find a specific part of it, I've broken it up into chapters to make that quite easy. However, if you're not sure of this topic area, or you're new to it, I would suggest watching through the whole video, because I'm going to try and explain at each stage how the theory matches with the experiment. So you'll have a really good understanding of why we're doing each thing that we do and what the results mean. I am also going to make a shorter video in the future on titration calculations, and this is to help with that kind of exam style question where you're just given a concentration and a volume of a solution and you have to work out the concentration of something else. But I'll do that in a future video. Now, if you'd like to follow along with the experimental bit, as usual, all the equipment is listed in the description box. And let's get started! In previous videos, we've just been considering a solution as either acid or base, and sometimes a neutral solution as well. But this isn't quantitative. It doesn't tell us how much acidity or basicity is present. So we need to understand that this is a sliding scale between acidic and basic, with neutral being right in the middle. If we take an acidic solution and add a basic solution, the final solution will be less acidic. But as in the example we just did, we didn't add enough to neutralise because the arrow isn't in the middle, so the solution is still weakly acidic. Another example would be a weakly basic solution to which we add an acid. But in this case we overshot the middle position because we added too much acid, and now the solution is weakly acidic. So we need a way to determine how acidic or basic something is. To understand these concepts better, we need to consider concentration. No, not thinking really hard, but instead how much of something we have in a given volume. We've come across this before when we made up a sodium bicarbonate base solution. I can't remember the exact numbers, but let's say I dissolved 5 grams in 20 millilitres. We can perform a division to work out how much we have in each milliliter. And as you can see, we have 0.25 grams per milliliter, which can be written neatly as grams per mil or grams per mil to the -1. Note there are lots and lots of ways to represent concentration. So in this one we used grams per milliliter, but sometimes people use things like a weight in a given volume, so it could be a kilogram in a litre, or it could be grams in a litre, but there's lots and lots of ways it can be represented. So, how can we use this information to measure how acidic or basic something is? Now, this is time to really concentrate, because if you get this, titration calculations and working with these kind of things becomes very easy. So let's take an unknown vinegar solution with acetic acid present, and that's this red solution here. We can measure out a known quantity of sodium bicarbonate and add it to the acid until the solution is neutral, and that can be seen as the droplets here. So it's gone neutral because it's gone green. We can then use the volume of the base, so that's sodium bicarbonate, that was required to calculate how many molecules of base were required, as we need to know the number of molecules. We know that 1 molecule of sodium bicarbonate can only react with 1 molecule of acetic acid. So the number of molecules of base that was required to neutralise it is equal to the number of molecules of acid present. That's really important. The fact that we can work out from the amount of base that we used how much acid was originally present. And we can use this to calculate the concentration. Now, I know that's been a lot of information, but that's basically what a titration is. It's just taking a known volume of an unknown acid or base and adding a known volume, again this known volume, of a base or added solution of known concentration until the solution is neutral. And this is where people can struggle quite a bit, because you've got a number of values to keep in your head or keep down on paper. The volume of the solution of your unknown sample, the volume required to neutralize your known solution, and the concentration of your known sample. Yes, and I almost forgot here that it's also essential to include an indicator, because how else will we know when we've added enough acid or base to neutralize the solution? Because a neutral solution can look as colourless as an acidic or basic solution. So we need to make sure we have an indicator in there to tell us when it's neutral. So I have two more brief points before we carry out our experiment. And this first one is on moles. Chemists love moles for a very practical reason. We care about molecules. Now, I've put up a reminder here about how to calculate moles, but if you'd like me to do a video on the subject, please leave a message in the comments. When we look at a chemical equation like the one I've shown here, we're interested in how many molecules interact with each other, and not the masses, because molecules have different masses. So it's not useful to think about something as a gram of something or a kilogram of something, because say a kilogram of protein and a kilogram of water have a great many different number of molecules. So it gets very confusing. Now, what we do is we use moles to solve this problem. So we can see in the reaction above that one molecule of sodium bicarbonate reacts with one molecule of acetic acid. So they react in a ratio of 1 to 1. It's very interesting as well, or very important to note that 1 mole doesn't mean just a single molecule. If we remember back to moles, it's the Avogadro's constant of molecules. So it's about 6 times 10 to the 23 molecules, an awful lot of molecules, because it's very hard to count individual molecules. Anyway, that's why you'll often see things represented as moles per litre or moles per decimeter cubed. That's just a fancy way of saying a litre, instead of grams per centimetre cubed or grams per milliliter, because it's a more useful measure when considering reactions. And don't worry, we're going to practice using these units in a titration calculation video that I'm going to put out a little bit later. Now, one quick word about accuracy. Whenever you measure something, you want to use an accurate tool, and typically a titration is carried out with a long glass burette, and that has a tap at the bottom and very carefully measured graduations so that you can do very accurate additions of small volumes of liquid or aliquots. However, I don't have one of these at home, and instead I'll be using a plastic pipette, which will give my experiment a very wide margin of error. But we can still see what happens, and we can still do these measurements even if they're not perfect. So let's crack on with the experiment. So we need to make the red cabbage indicator, and I'll link that video. And then what we want to do is we want to prepare a 0.5 molar stock of sodium bicarbonate, but I only want to make about 20 millilitres of that stock, so I'll need to dissolve up 0.84 grams of sodium bicarbonate or bicarbonate of soda in 20 millilitres of water. So we'll weigh that out, and you'll need a spatula. We'll weigh it out very accurately with this balance. And you'll see when the dial gets to 0 that we know we're spot on there. Lovely. We'll put that into a beaker. And then we're going to make use of this volumetric, they're very accurate pieces of glassware. And this one's for 10 millilitres. So I'm going to use it twice for this. And all I'm going to do is I'm going to fill that up with some distilled water up to that line. Oh, got to take a little bit out. Add that in. There we go. Add that in, and then I'll do it again to give us our 20 millilitres that we're dissolving in 0.84 grams of sodium bicarb. And that gives us our base solution, our known base solution. Now I've got some malt vinegar here, but it's too concentrated as it is. So what I'm going to do is take 2 millilitres of it, put it into this volumetric flask, and then make it up to 10 millilitres. Oh, I overshot a little bit there. Oh dear. And then I'm going to put in 10 more millilitres, so we've diluted our vinegar by 2 millilitres into 20, and I'm adding the indicator into this second solution just to help make that up and have a really nice strong solution with the indicator in, so it's very, very clear to see what's going on. Look at that lovely reddy pink that shows we've got an acid present. So now I've got my base solution, my acid solution, and I've got next to them just a standard so I can see when we get to neutral. So there's the first addition in our titration, and we're just going to slowly, mixing in between each addition, add 1 milliliter at a time. And every time we mix, it's just to see if that colour is getting closer to our neutral solution colour next to us. Now I don't know why, but on the camera the neutral solution looks a lot bluer than it does in real life. It's sort of more of a, it is a kind of blue, but it's a deep purpley sort of colour. So I'll stop the titration, and I've noticed it looks ever so slightly red still on screen. Oh, I had to add a bit more indicator because my neutral solution wasn't, it was a bit paler. And you'll see when I stop the titration on the camera, it still looks a little bit purpley in the reaction vessel. And this is now the 8th addition. This is 8 millilitres of that 0.5 molar base solution. And that is done. We've got it to neutral, so we know we needed 8 millilitres. So, let's work through this calculation together. We can see the equation above for the sodium bicarb plus acetic acid. We just have one molecule reacting with one molecule. Now let's think about what we know. Well, this is where things can get a little bit tricky. I'm going to start with the second two. We've got the concentration of the base. We made up that solution, so we know it's 0.5 moles per decimeter cubed, or moles per litre. And we know the volume of the base we needed in the titration was 8 millilitres. We had to add 8 millilitres to get to neutral. The volume of the acid, however, I know we made up a solution that was in total 20 millilitres. But remember, we were diluting 2 millilitres of acid. So if you wanted to know the concentration of acid in that 20 millilitres, well, you could use the volume as 20 millilitres. But I don't want to know that. I want to know the volume of acid in the original vinegar. So I need to think about all the molecules of acid only actually came from the 2 millilitres of acid we added. So now we need to calculate the moles of the base so that we can work out the moles of the acid, and then we can work out the concentration of the acid. Now, we can use the equation moles is equal to volume times concentration. And if you ever forget this equation, just have a look at some of the units for different things. If you look at the concentration of base, the unit is mole per decimeter cubed, or per litre. So you know that concentration is equal to moles divided by litres, or moles divided by volume. And you can rearrange that by simply timesing both sides by volume to get moles is equal to volume times concentration. So the unit actually tells you the equation. It's a very handy little trick. Anyway, let's work through this. So moles equals volume times concentration, and we need to convert that volume into litres, or decimeters cubed. So the volume of base we needed was 8 millilitres, which remember there are 1,000 millilitres in a litre, so 8 millilitres is equal to 0.008 litres. It's very important that you can do those sort of transformations, and don't get hung up on it. Just remember that if you were to say 0.001, then 1,000 of those go into 1, and you can think about numbers like that. It works very nicely. So we'll times this together, and you can see how the decimeters cancel, and we end up with 0.04 moles. Now what's very interesting here is in this particular equation, the moles of the acid are equal to 1 times the moles of the base, because it's a 1-to-1. So we can say the moles of the acid is 0.004 moles. That was super easy. And now we can calculate the concentration of the acid. And in fact we can use that thing we said before, mole divided by volume. Super easy. So we can take 0.004 moles, and we're going to have to remember, always change your volume to litres. Otherwise what you're calculating is the concentration per milliliter, and it would be, 0.5 moles per milliliter instead of per litre. So we need to remember always to change those units. 0.004 moles divided by 0.002 decimeters cubed, and that will give us 2 moles per litre. So the concentration of acid is 2 molar, or 2 moles per litre. Now that is a bit high, I have to say, for a vinegar. That works out to be about 12%, and normally the malt vinegar is about between 5 and 8%, I think. I couldn't find this particular brand, but that is a little bit high, and it's most likely because of the error in the experiment. Thank you so much for watching. I hope you found that video useful. I will be putting up a video about calculations with titrations later on, and if you like this sort of content, why not subscribe and push the thumbs up button if you enjoyed it too, because that helps the channel. And I'll see you later. Bye!